Synaptic transmission involves the release of neurotransmitter from the presynaptic cell, diffusion of neurotransmitter across the synaptic cleft, and binding of the neurotransmitter to receptors on the postsynaptic cell. It ends when the neurotransmitter dissociates from the receptor and is removed from the synaptic cleft. Your goals for learning are to understand the detailed mechanism of neurotransmitter release, diffusion, and binding to the postsynaptic receptor. To learn that the action of the neurotransmitter depends on the type of receptor on the postsynaptic cell. To review the location and function of neurotransmitters. Here's what you need to know. The difference between the central nervous system and the peripheral nervous system. The anatomy of the somatic motor system. The anatomy of the peripheral autonomic nervous system. What glial cells are. To see definitions of terms, click the bold red words. We have examined the anatomy of a synapse. Now let's look at the details of synaptic transmission. Click the presynaptic neuron to produce an action potential. An action potential in the axon terminal causes voltage-gated calcium channels to open and calcium to enter the terminal. Click the presynaptic neuron again to see the calcium channel in action. The presence of calcium inside the cell causes the synaptic vesicles to fuse with the membrane. Each vesicle releases a fixed amount of neurotransmitter into the synaptic cleft. Neurotransmitter diffuses across the synaptic cleft. Click a synaptic vesicle to observe this process. Neurotransmitter binds to a receptor on the postsynaptic neuron where it can act directly or indirectly. Click the postsynaptic neuron to observe a neurotransmitter binding directly to an ion channel. Chemically gated ion channels remain open as long as the neurotransmitter is bound to the receptor and are not sensitive to changes in the membrane potential. Synaptic current, or ion movement through chemically gated channels, may depolarize or hyperpolarize the neuron. The example below illustrates depolarization of the postsynaptic neuron. Synaptic transmission ends when the neurotransmitter dissociates from the receptor and is removed from the synaptic cleft. Click the neurotransmitter to see a simplified version of this process. Most often, the neurotransmitter is pumped back into the presynaptic terminal or into nearby glial cells. Here we illustrate the neurotransmitter glutamate being pumped back into the presynaptic terminal. In some cases, the neurotransmitter is broken down by enzymes, and the breakdown products are taken up by the presynaptic cell. The neurotransmitter acetylcholine is an example of this process. When breakdown products are transported into the presynaptic terminal, they are used to resynthesize neurotransmitter. The neurotransmitter, which is being returned to the terminal, is repackaged into vesicles for storage and subsequent release. Click the presynaptic cell to see neurotransmitter repackaged and stored in vesicles. The mechanism by which neurotransmitter is returned to the terminal is specific for each neurotransmitter and can be selectively affected by drugs. To review all the events of synaptic transmission, click the presynaptic neuron. An action potential occurs in the presynaptic terminal. The voltage-gated calcium channels open and calcium diffuses into the axon terminal. The synaptic vesicles fuse with the presynaptic cell membrane and open. Neurotransmitter diffuses across the synaptic cleft and binds to the postsynaptic receptor. Current flows across the postsynaptic cell membrane. Neurotransmitter dissociates from the receptor and is pumped back into the axon terminal. Click the presynaptic terminal to view the animation again. We have examined the mechanism of synaptic transmission. Now let's look at the consequences of synaptic activity on the postsynaptic cell. The action of the postsynaptic cell depends on which neurotransmitter is involved and the specific receptor found on that cell. Receptors that bind acetylcholine are called cholinergic receptors. There are two families of cholinergic receptors. One family is also activated by the chemical nicotine, and the other family is also activated by the chemical muscarine. Within each family, there are multiple receptor subtypes for each neurotransmitter. Each subtype may have a different effect in the postsynaptic cell. Drag the acetylcholine to the receptor that binds nicotine. The nicotinic cholinergic receptor, or NACH receptor, is the ion channel found at the neuromuscular junction. At this receptor, acetylcholine acts directly to open these channels, producing a fast, excitatory postsynaptic potential. Acetylcholine is excitatory at nicotine receptors. It causes skeletal muscles to contract. Drag the acetylcholine to the excitatory receptor that binds muscarine. Some subtypes of muscarinic acetylcholine receptor, or MACH receptors, are found in the central nervous system and on most effector organs of the parasympathetic branch of the nervous system. Acetylcholine acts indirectly at these receptors, producing a slow, excitatory postsynaptic potential. Acetylcholine is excitatory at these muscarinic receptors, causing neurons to fire action potentials and smooth muscle to contract. Drag the acetylcholine to the inhibitory receptor that binds muscarine. Other subtypes of MACH receptor are found in the central nervous system and in the heart. Acetylcholine acts indirectly at these receptors, producing a slow inhibition of the postsynaptic cells. In the heart, this effect decreases heart rate. Acetylcholine is inhibitory at these muscarinic receptors, causing postsynaptic cells to hyperpolarize and the heart to slow down. The action of acetylcholine may be excitatory or inhibitory. The effect depends on which receptor is present on the postsynaptic cell. There are two families of receptors for the neurotransmitter norepinephrine, alpha receptors and beta receptors. Each family member is identified by its letter and a number. These are called adrenergic receptors, and norepinephrine acts indirectly when binding to them. Both alpha and beta adrenergic receptors are found in the central nervous system, and more importantly, on effector organs of the sympathetic nervous system. Drag the norepinephrine to the alpha-1 receptor. Norepinephrine acts indirectly at alpha-1 receptors to produce slow excitation. This causes smooth muscle to contract. Alpha-1 receptors are located on blood vessels, which supply the skin, mucosae, and abdominal viscera. Norepinephrine is excitatory at alpha-1 receptors. Drag the norepinephrine to the beta-1 receptor. Norepinephrine also acts indirectly at beta-1 receptors in the heart to produce slow excitation. Heart rate and strength of contraction increase. Norepinephrine is excitatory at beta-1 receptors. Drag the norepinephrine to the beta-2 receptor. Norepinephrine acts indirectly at beta-2 receptors to produce a slow inhibition. Beta-2 receptors located on the respiratory airways and blood vessels that supply skeletal muscle and heart cause dilation. Epinephrine from the adrenal medulla is more potent than norepinephrine, and both are inhibitory at beta-2 receptors. The action of norepinephrine may be excitatory or inhibitory. The effect depends on which receptor is present on the postsynaptic cell. We have learned that acetylcholine and norepinephrine are found in the central nervous system and at effector organs of the nervous system. On the next few pages, we will review the location and function of these neurotransmitters in the peripheral nervous system. Then we will look into the central nervous system to learn the functions of these and other neurotransmitters. Click the somatic motor neuron. Motor neurons of the somatic nervous system release acetylcholine. They are cholinergic. Skeletal muscles bear NACH receptors. Thus, the action of acetylcholine on skeletal muscle is direct, fast, and excitatory. Click the first sympathetic neuron. The first of two neurons in the sympathetic chain, the preganglionic neuron, is cholinergic. Click the first parasympathetic neuron. The first of two neurons in the parasympathetic chain, the preganglionic neuron, is also cholinergic. The second neuron, or ganglionic neuron, in both the sympathetic and parasympathetic chains, has NACH receptors. Thus, the action of acetylcholine on ganglionic neurons is direct, fast, and excitatory. Click the sympathetic ganglionic neuron. Sympathetic ganglionic neurons release norepinephrine. They are adrenergic. Click the parasympathetic ganglionic neuron. Parasympathetic ganglionic neurons release acetylcholine. They are cholinergic. Both acetylcholine and norepinephrine act indirectly on the effector organs of the autonomic nervous system. Their action is slow, sometimes excitatory, sometimes inhibitory, depending on which receptor is found on the effector organ. Glutamate is the most common and most potent excitatory neurotransmitter in the central nervous system. Glutamate acts directly on ion channels that permit passage of both sodium and potassium, producing fast excitatory postsynaptic potentials. Click the glutamate fibers to see this effect. The major inhibitory neurotransmitters in the central nervous system are GABA and glycine. Click the GABA fibers to see the effect they have on excitatory transmission in this neuron. Like GABA, glycine binds to receptors which directly open chloride channels, producing fast inhibitory postsynaptic potentials. Click the glycine fibers to see the effect they have on excitatory transmissions in this neuron. Click any of the fibers to see the animations again. The rapid signaling of directly acting neurotransmitters is important for sensory motor coordination, communication, and many other higher functions. Click the buttons to observe behaviors associated with directly acting neurotransmitters. Rapid synaptic signaling is essential for coordinating sensory input with motor output, especially during athletic performances.
The macula densa cells in the juxtaglomerular apparatus of each nephron function as osmoreceptors.
Rapid synaptic signaling is essential for speech and other forms of communication. Playing music requires rapid synaptic signaling. Click the buttons to observe behaviors associated with the action of indirectly acting neurotransmitters. All of the neurotransmitters at effector organs of the peripheral autonomic nervous system act indirectly.
Honey, breakfast is ready.
Norepinephrine, acetylcholine, and serotonin, another central nervous system neurotransmitter, all produce state changes in the central nervous system. One important example is the change from the sleep state to wakefulness to attentive arousal.
Medial condyle, lateral condyle. Greater trochanter, lesser trochanter. Greater trochanter, lesser trochanter. Medial, no, wait, okay. Medial condyle, lateral condyle. Greater trochanter, lesser trochanter.
Theories of learning and memory often invoke the action of indirect neurotransmitters to explain changes in synaptic activity. Indirect neurotransmitters can modulate neurons, ultimately changing their channel functions and producing a new and different output. Here's a summary of what we've covered. Neurotransmitter is released from vesicles in the presynaptic cell and binds to receptors of the postsynaptic cell. Neurotransmission ends when the neurotransmitter dissociates from its receptor. The effect of the neurotransmitter on the postsynaptic cell depends on the receptor, not the neurotransmitter molecule. Acetylcholine and norepinephrine are the most important neurotransmitters in the peripheral nervous system. Glutamate, GABA, and glycine are the most important neurotransmitters in the central nervous system. Fast and slow synaptic activities serve different functions. To access cross-references for this topic in your Benjamin Cummings textbook, click here. To test your knowledge, click the quiz button to go to the self-quiz.